We know that we can represent a power series as a function, but we can also take some functions and represent them by power series and use some of the properties of power series to do that. So one of the common examples of this would be, like, for example, the sum from 0 to infinity of a times r to the nth power. We know that that is a geometric series, and we know that it evaluates to a over 1 minus r. So if we can take that and work backwards, we could take something like 1 over 1 minus x and allow that to be a power series. So this says to find a power series for this function centered at 0. So to put this in that format, a over 1 minus r, I would have a equal to 1 and I would have r equal to x. So f of x, which is 1 over 1 minus x, could be written as the sum from n equals 0 to infinity of 1 times x to the nth power, or just the sum from 0 to infinity of x to the nth power. Now, of course, there is a limit to this because it's only valid for certain values of x, the ones that would make this converge. So if we wanted to figure that out, we would set u sub n to be x to the n. We would set u sub n plus 1 to be x to the n plus 1, and then you could do the ratio test and find out that the limit as n approaches infinity of x to the n plus 1 over x to the n, which ends up being the limit as n approaches infinity of x, or just the absolute value of x, would have to be less than 1. Or you could use the geometric portion and say that x has to be less than 1 because r has to be less than 1, the absolute value of that. So x can only be in the interval from -1 to 1. And of course you'll find that that the endpoints don't work on this one as well, because that would make the series diverge. So this is only valid for x in the interval from -1 to 1. And that's important to realize, is that it doesn't work for all values of x necessarily. In this case, it's only for -1 to 1, not including the endpoints. But this is how you would represent this as a series centered at 0. So what if you didn't want 0? What if you wanted something like c equals -1? Well, we could do that too. We're just going to have to do a little bit of work on it. So a series centered at c equals -1. To make it fit the format that I want, I need something equivalent. So I'm going to, and I want it to say x plus 1 here, because that would be x minus -1. So in order to cancel out that -1, I need to have another 1 out front. So if I put a 2 here, these two are equivalent because we would have 2 minus x minus 1, which would be the same thing as 1 minus x. Well, it doesn't fit that a over 1 minus r format that we're trying to get it to yet. So basically, we need a 1 to be right here. And in order to do that, I could multiply the whole denominator by 1/2 and the whole numerator by 1/2. So this would give me 1/2 divided by 1 minus x plus 1 over 2. And if that is equal to a over 1 minus r, a would be 1/2, r would be x plus 1 over 2. So this would be equal to the sum from 0 to infinity of 1/2, that's a, r to the nth power, x plus 1 over 2 to the nth power. And because this is understood to be 1/2 to the first power and this is 1/2 to the nth power, you could write that as 1/2 to the nth power, n plus first power, and then x plus 1 to the nth power. Now, of course, you do need to figure out where this is valid. So in this case, I would have the r, which was the x plus 1 over 2, going back to the original r. Since it's geometric, I would need that to be less than 1. So x plus 1 over 2 would be between -1 and 1, which means that x plus 1 would be between negative 1 and 2, or x between negative 3 and 1. And because it is a geometric, and we know that we have to have the absolute value of r less than 1. Now you could check the endpoints here. If you plugged in the negative 3, you would have 1/2 to the n plus 1, and then you would have a negative 2 to the nth power. If you plugged in the 1, you would have a 2 to the nth power. So in this case, you're not looking at your endpoints being a problem. So this would only work for the interval from negative 3 to 1. Let's look at another example. It says find a geometric power series for f of x equals 1 over 3 minus x centered at z equals 1. So we're going to do a similar kind of trick to what we pulled before. I want to have centered at z equals 1, so I want to have an x minus 1 in this denominator. So what I'm going to do is I'm going to break the 3 into a 2 plus 1. And then instead of having 1 minus x, I'm going to have minus x minus 1. And you can see that that would end up being the same thing if you distributed the negative. And just like last time, I want this to be a 1, so I'm going to multiply by 1/2 and 1/2. So that'll give me 1/2 over 1 minus x minus 1 over 2. And this is now in the a over 1 minus r format, where a equals 1/2 and r equals x minus 1 over 2. So this is going to be equal to the sum from n equals 0 to infinity of 1/2 times x minus 1 over 2 to the nth power, or 1/2 to the n plus 1 times x minus 1 to the nth power. So this is my power series. And if I were to set the absolute value of r, which is the absolute value of x minus 1 over 2 less than 1, you could see what would happen. We would have x minus 1 over 2 between negative 1 and 1. X minus 1 would be between negative 2 and 2, or x between negative 1 and 3. And then we could check the endpoints by plugging them in. At this one, we would have, just going back to whichever version of this you want to, at x equals negative 1, we would have the sum from n equals 0 to infinity of 1/2 to the n plus 1 times negative 1 minus 1 would be negative 2 to the nth power. And basically what ends up happening here is we have the sum from 0 to infinity of negative 1 to the nth power, and then the 2's cancel out, so we get 1/2 to the nth power. And this one, or actually, no, just 1/2 because the nth doesn't cancel out. And this one's going to diverge because it just keeps adding and subtracting the same amount. And if you let x equal 3, you would have the sum from 0 to infinity of 1/2 to the n plus 1 times 2 to the nth power. So it's the sum of basically 1/2, so that diverges as well. So this is true for x in the interval from negative 1 to 3. Now you can also do operations with power series. So if you had something like two power series, a n x to the n and b n x to the n, you can multiply by a scalar multiple, you can raise them to a power, and what ends up happening is the little n for x to the n gets multiplied by the big power of n. So basically just raising the inner parameter to a power. You can add or subtract them as well, and all that does is add or subtracts the series coefficients. So let's look at what that might look like. It says find a power series for the function 4x over x squared plus 2x minus 3 centered at c equals 0, and find the interval of convergence for the power series. So when I see something like this, the first thing that comes to mind is partial fractions, because I've got something in the denominator that will factor, and I know that if I can get this down to linear denominators, then I can work with it and make a lot more sense. So I'm going to do the partial fraction decomposition and figure out what those would be. So hopefully we're comfortable with this process now. I just worked through it, but I just found the a and b that goes over the two factors, x plus 3 and x minus 1, and I get f of x equals 3 over x plus 3 plus 1 over x minus 1. So if you need to pause the video and work your way through that, feel free to go ahead. Otherwise, let's go ahead and move on. So I'm gonna play with both of these and make them into a power series centered at 0. So to do that, I'm going to first try to get it into something minus x instead of plus x or whatever we have going on here. So here, I'm going to write this as 3 minus a negative x, because that allows me to have the minus here, and we'll work with that one in just a second. And with this one, I'm going to multiply the top and the bottom by a negative 1 so that I can have 1 minus x in the denominator. Okay? So this one's pretty much done on the right. This one right here we need to do a little work in because I need a 1 here. So I'm going to multiply by 1/3 on the top and the bottom. And I will get 1 over 1 minus negative x over 3. And then here I've got the negative 1 over 1 minus x. So these are both in the format that I want them to be. For the first one, my a is going to be 1, so I'll have the sum from 0 to infinity of 1. My r is going to be negative x over 3, so I'll have negative x over 3 to the nth power. For this one, let's just bring down the negative, and we'll have a equals 1. And we'll have r equals 1 minus, or sorry, r equals just the x. So we'll have x to the nth power. So it's ar to the n, ar to the n. Okay? So writing this in that more power series form, we could have just, let's see, you could bring out the negative 1/3 to the n, and then have x to the n. And if you needed to actually simplify this a little bit further, you can do so, and you'll have the sum from 0 to infinity of, let's just make this, let's factor out the x to the n, and we'll have negative 1/3 to the n minus 1 is how we would write that. X to the n. Now, of course, we need to figure out the interval of convergence here. So I'm going to take it one at a time. I'm going to take the sum from 0 to infinity of negative x over 3 to the nth power. That's a geometric, and we know that that for that one, r has to be less than, or the absolute value of r has to be less than 1. So the absolute value of negative x over 3, or which will end up being positive x over 3, has to be between negative 1 and 1. So that tells me x has to be between negative 3 and 3. And if it is a greater than or equal to, then you don't have to worry about that with the geometric, because the greater than or equal to 1 diverges. So it couldn't be the endpoints there. And then with the other one, 0 to infinity of x to the n, of course we know that the absolute value of x has to be less than 1. So x is between negative 1 and 1. So the intersection of these two is going to be the most restrictive version of it. So if we've got, we've got this set, and then we've got this set, we're only looking at the negative 1 to 1. So this is true for x in the interval from negative 1 to 1. And that would be our power series. This example says use the power series 1 over 1 plus x equals the sum from n equals 0 to infinity of negative 1 to the n x to the n to determine a power series centered at 0 for this function, which has been broken down into partial fractions 1 over 1 plus x plus 1 over 1 minus x. Well, the 1 over 1 minus x centered at 0 is pretty simple because that's just going to be the sum from 0 to infinity of 1, which is a, r to the n, so that'll be x to the n. So that one's already pretty much done for us. So we know that if we've got this sum from 0 to infinity, negative 1 to the n, x to the n, and then we're going to add the sum from 0 to infinity of just x to the n, okay, what we end up with is if we factor out the x to the n, we'll have negative 1 to the n plus 1. And the interval convergence for both of these, because it's just x to the n, is going to be negative 1 to 1, because that absolute value of x has to be between, or just x has to be between 1 and negative 1. So there you go.